All right, so as you take a look at this graph, where do you think it's not continuous?
Yeah. X equals 5.
X equals 5? Yes, I would say that is a good one. At x equals 5, it is not continuous. Good. Where else is it not continuous?
With anywhere that there is an open space.
Yep, so at 3, it is not continuous. Yep, and also, yes, at 1, it is also not continuous. And so, if we know that it's not continuous at each of those 3, what is happening at each of those values? Because we actually have different ways that we need to describe things that are not continuous. We call them discontinuities, the points at which it is no longer continuous. So a little bit specific here. There were 3 of them. Between these 2, we notice kind of the same thing happening, right? What is present at those 2 points? Yep, that open circle, the hole in the graph. Exactly. And we're going to consider that a different type of discontinuity than the one that happens here at 3. Because you notice 3, it's kind of like it's just skipping a bunch. We call that a jump. It is like the graph is jumping from this point all the way up to this point here. And so these are the different types of discontinuities that you're going to be seeing and the ones that we'll be talking about as we go forward. These would be good to go into your notes. So these 3 different types here, we have a jump. So you notice like the graph is going along just fine, but then we got to pick up our pencil in order to get to the next part. Anytime we have to pick up the pencil to get to the next part there, that means the graph jumped. And so it's not continuous. An asymptote, like a jump but slightly different, because the asymptote, it continues on for infinity. It's approaching whatever that number is from both sides. And it gets it as close as we could possibly ever desire, but it never actually reaches it. So there actually is not a point where the asymptote is. So that's considered to be a discontinuity as an asymptote. Right, and then the other one is the one that we mentioned earlier. If there's a hole in the graph, that is considered a discontinuity as well. One little side note on that, because it comes up on the homework. Hole is just another word for the more long and drawn out, removable discontinuity. They mean the same thing, hole and removable discontinuity. Why would you want to say one rather than the other? Well, because you want to sound fancier by saying removable discontinuity instead of there's a hole. But it means the same thing. And then you'll notice up above there we have an informal definition of continuity. So informally here, a function is considered continuous at a point. Notice it's specifically talking about at a point if the graph is connected there. So basically we're going at it from the left, we're going at it from the right, and we're meeting at the same place. So it's not continuous then if the graph has a hole or a break at that point. Or by break we could also say jump. So if there's a hole, or if the graph jumps there, or if there's an asymptote, then we know that it is not continuous at that point, and so that is a discontinuity. So this informal information, it's all here just so you can just glance at a graph and have a pretty good idea, would I consider this to be continuous or not at this point? But we do have to get into some formality as well. We have to be able to prove it and be able to say yes it is or no it isn't, and be able to actually support that as well. So now we have to get into some formal definitions. So this is our definition of if it is continuous at a number. And again, notice, and please include this in your notes, this is continuous at a specific number, which they're calling A. So only at a point. This is not saying the whole graph is continuous, just that it's continuous at that point. So now we can go ahead and take a look at this graph, which has lots of discontinuities going on in it, right? And see what are the continuities, like where are they located, what are the x values, and then what type of discontinuity is it. So take a minute here, look over the graph, and for each point where there's a discontinuity, tell me what type it is. So this is the formal rule that you just wrote into your notes. And so let's actually see how this would apply. So like, where's our first discontinuity look like it's at? I'd say it's here at -2, right? So at -2, if I'm looking for the limit as x approaches -2, from the left, the limit that that's approaching is whatever this y value is here. We don't have a y scale, but we know it's that. All right, if I'm approaching from the right side to find that limit, then I'm approaching this y value. So that tells me that the limit as x approaches a of f of x at -2 is that it does not exist. There is no limit there. And since that limit does not exist, it cannot possibly equal f of a. And so that's why we could then conclude and actually prove and support it with the mathematics there why that's a discontinuity. Now, of course, did you have to go through all that to recognize that as a discontinuity? No, you just looked at it, right? And when you looked at it, you said, hey, that's a discontinuity, and it is a, what type of discontinuity?
Jump.
It is a jump, yes. So we have a jump discontinuity there at -2. All right, let's take a look at the others here. We should also have discontinuities at 2, 4, and 6. Most of those are jumps. Which one is not a jump?
4.
Yep, 4. 4 is not a jump. What type of discontinuity is 4, or at least does it appear to be? Yep, looks like it's an asymptote. So these over here are our discontinuities. We have jump, jump, asymptote, and a jump. Now, a little side note here. What about those two? What about at -4 and at 8? Well, they're the endpoints. Technically, those are the edges of the domain of this graph. And because of that, they aren't considered to be a discontinuity because it just happens to be that that's where the graph ends. A discontinuity really has to be saying we're going from something to something else. That instead is just an endpoint. All right, then next up, another set of notes. And again, these are being very precise with some of the things they're saying. Make sure that you write down everything as you see, although technically you don't really need to write the 7 or the word theorem, but everything else, write it out exactly as you're seeing it. Because there's some little details in the words that we're going to be looking at and talking about going forward that are going to matter a lot more than you might at first suspect. So as you take a look at this, I said there's some details in here that can prove really significant. And I want to actually bring one of those out for you. I'm going to go to a rational function, just because it's a nice, tangible example. And I'm going to go with a super simple one, just 1 over x. Imagine the graph of 1 over x. Is that continuous over every possible x value you can think of? No, it's not, right? Where would it not be considered to be continuous?
At x equals 0.
Yeah, at x equals 0. At x equals 0, we have an asymptote, right?
Heck yeah.
Okay, so then if I take a look up at my notes, though, it just said that all of these types of functions are continuous, and yet I just said that one's not continuous at 0. Why is that? It's a little detail in the wording. Notice it says these are all continuous at every number in their domains. What is the domain of 1 over x? And so notice our domain doesn't include 0. And so the one point where we could say, wait, it's not continuous there. Well, yeah, that's because that's not part of the domain. These functions that are listed are all of them where it's actually continuous within the domains of the function. If it's not part of the original domain, we can't talk about if it's continuous at that point there. So then why do we bother with listing all these out? Basically this, if I were to summarize this in a much shorter way, I could say for any single function family, it should be continuous at every number in its domain. The time when it won't be then, because that's probably the question then, well, okay, well then when wouldn't it be? Piecewise functions. And piecewise functions are where we start getting jumps that start happening. We start getting holes that behave oddly. And so that's really where you're going to be seeing some of the different behaviors and some of the discontinuities within the graphs. All right, now with that established, we're also going to be taking a look today at continuity from the right and from the left. Notice it mirrors the same rule you wrote down earlier. It's just that the limit is from the right or from the left. But otherwise, it's the same basic rule. Seems super simple, but there can be some that trips people up on it. So add this to your notes as well. All right, so now it's time to actually apply the rules that we've gotten on is it continuous or not. So for that graph, I'd like you to please answer those three questions. Is it continuous at 2? Is it continuous from the left at 2? And is it continuous from the right at 2? And don't just go answer, answer, answer. Actually think about each one, because one of them has a tendency to trip people up if you just go through it too quickly. All right, so let's see here. For that first one, is it continuous at 2? No. We can actually see that pretty quickly, right? Because we can just look and say, wait, there's a jump there. The answer is no. Well, what about, is it continuous from the left at 2?
Yes.
Well, as I follow it along from the left, I'm actually going to apply my new rule here, the one that I just put down to my notes. I'm looking to see the limit as x approaches 2 from the negatives of f of x. In this case, f of 2, or no, x. Does that approach the value of f of a? Well, the limit as x approaches 2 from the negatives, notice it's approaching 3. The value of f of a is, and in this case actually I should be more specific, a here is 2. So the value of f of 2, the value of f of 2 is 3. So that's why it's a yes. Now, why do I go through all of that? Just to say something that most of you looked at and were like, oh yeah, the answer is yes. Because now we're going to take a look at this last one, which can sometimes be the one that trips us up. Because in this case, we're looking for the limit from the right side. So in this case, then, that means the limit as we approach 2 from the right. Well, what is the limit as we approach 2 from the right? 1. And f of 2 still equals 3, though. And so, does the limit equal the actual value? No, it doesn't. And so that's why we would say it is not continuous from the right. Basically, the idea is that it's the one that we're actually approaching that has the solid dot that we can use. Because we have the solid dot here, whichever way we're approaching that from, that's the one where it can be continuous from that side. With the open dot there, well, we're definitely not approaching the actual f value at that point. Okay. This is the last problem we're doing together. After the last one we did, this one should go pretty quick. Please decide for each of these two x values, is that graph continuous from the left or is it continuous from the right? All right, first one, at x equals 1 here. Is this one continuous from the left or the right? The right, absolutely. Because you'll notice that as I go down to from the right, I'm approaching the actual value. The actual g of 1 value would be 1. So it's the one that's approaching 1, that's from the right. Basically, I'm looking for that solid circle. And so if I'm looking for that solid circle, at x equals 3, am I approaching it from the left or the right? Well, see where the solid circle is? I'm approaching that from the left, so yes, it is from the left there.